Hi, I'm Nick Rhinehart, and today I'll talk about some of my research that I did at UC Berkeley. None of the content of this talk is based on my work with Waymo, which I very recently joined as a senior research scientist. Okay, so I'll mainly talk about two papers today, and they're both about contingency planning. In order to explain what contingency planning is, first I'll walk us through a situation that it's useful for. So here, this robot driving this car is trying to make an unprotected left, in which it does not have the right of way in the intersection. And this oncoming car, which we say is uncontrolled by the robot, let's say it's driven by a human, this oncoming car may or may not yield to the robot if it tries to turn left. So the decision tree I'll show to you now represents possible sequences of robot and human decisions. So first, if the robot decides to wait outside the intersection, the other car deterministically passes through the intersection, and then the robot turns and arrives late, and we'll say it receives a return of 0 in this case. Alternatively, if the robot decides to enter the intersection slowly, the human-controlled car may or may not yield to the robot, and then the robot either passes through the intersection first to arrive on time and receives a return of 1, or it passes through the intersection second to arrive late and receive a return of 0. Finally, if the robot decides to enter the intersection aggressively, the human-controlled car may or may not yield to the robot again, and the robot either arrives early, receiving a return of 2, or the human-controlled car can't brake in time, and the result is a near collision, and the robot receives a return of -100 in this example. So let's think about how the robot could plan and achieve high return in this situation. If the robot had to plan a fixed sequence of actions ahead of time, that is an open loop, non-contingent plan, it would prefer to wait outside the intersection and never arrive early because of the unresolved human stochasticity. So it would accurately predict the value of its plan to be 0, and I'm denoting its value prediction as capital V hat here, and the true value of its plan as capital V. So if this robot has a good model of how the human behaves, it would, and is forced to produce a non-contingent plan, that plan would yield it or cause it to be very cautious. If the robot was overly confident in its ability to make the human yield, it would produce a plan that always turns before the human and predict that this plan would yield it a value of 2. But this value prediction would be an overestimate, when in reality, the human does not yield 50% of the time, leading to a true value of -49 for this plan because of the high cost of near collisions. Finally, with a closed loop contingent plan, so a policy, the robot can potentially arrive earlier by planning to enter the intersection first with a contingency plan for different behaviors it may observe the human to do. So it would accurately predict this contingent plan's value to be 0.5, which is higher than the real value of any other plan. If the human chooses to yield, the robot would proceed to make the turn. Otherwise, the robot waits for the human to pass. So in order to enable planning based on what other agents may do, we need a model of multi-agent behavior. Here's what we want our model to do. We have as input to our model a single latent robot plan, so basically a representation of the robot's planned policy, as well as some scene conditioning, so information about the current surroundings of the robot. And then the model incorporates as input uncertainty about what the other agents may do. So we're not going to be deterministically predicting what other agents are doing. We have some uncertainty. For one realization of what the other agents or what the sources of uncertainty in the environment may do, the single robot plan results in a specific joint trajectory. And for a different realization of what the other agents may do, the single robot plan results in a different joint trajectory. So if we can design a model in this way, the challenge of contingent planning is reduced to the challenge of identifying a single robot plan in the planning space that results in high-quality trajectory space plans. So we designed our model of multi-agent behavior based on an existing model of multi-agent trajectories that can be used to compute exact probability densities of joint trajectories. This is the precog model from my paper at ICCV 2019, which uses a normalizing flow as a learnable transformation from a base space of Gaussian random variables to the joint trajectory space. We needed this property of computing likelihoods in order to use the model's probability as part of a planning criterion, which I'll talk about later. So a two-agent version of this model is shown here in this diagram, although the model can generally be used for a variable number of agents. The way this model works is that it allocates uncertainty for each agent's decision at every step in time and conditions each of these uncertainties based on the temporally available information. So it factorizes uncertainty over agents and over time. The z variable at each time step, which I'll call latent variables, although they're not technically latent variables, they correspond to an agent's control of the next action that it can take. Each position depends on the control. So each predicted position in the model depends on the control, the z, and the most recently predicted positions of itself and all other agents. So in our two-agent model, if we decide latent values for one of the agents, let's say our robot car is agent 1, then we've decided how the robot will react to what it sees in the future. So in order to perform basically conditional or planning, we essentially want to choose values for the robot z's that take into account the robot's goal in this scenario. So we designed a planning procedure by doing some algebra to a planning posterior over the robot's decisions that takes into account the robot's goals g. So if we apply Bayes' rule, drop constants and lower bound it, we get a final optimization problem in terms of two distributions. For these two distributions, we use our learned multi-agent density function as a prior and a user-specified goal likelihood, which represents the probability that the joint trajectory satisfies some goal. So this goal likelihood includes some of the terms that you would use in a standard motion planning cost function, like a distance penalty to the robot's intended destination, as well as potential constraints, like maintaining a gap distance to the other agents. But this prior, this first term, comes from the model, and it essentially gives plans an extra bonus for resulting in jointly likely behavior. And we approximately solve this optimization problem at planning time using stochastic gradient ascent. We built several scenarios that require contingent planning in the CARLA simulator and collected data from each outcome in a variety of locations to serve as the training data for the model. So I'm going to show you videos from this first scenario, the overtaking scenario. Here, the robot is trying to overtake a human-driven car by first switching into the left lane and then passing it and then moving into the right lane. So while the human driver may slow down to facilitate the overtake, as shown here, in this other outcome, the human could also choose to speed up to prevent the overtake, as shown on this bottom left video. The robot should then yield to the person and then stop trying to overtake them. Or the robot could try to aggressively pass the human without seeing if they'll yield, as shown in the top video. But sometimes the human can't react in time, which results in an outcome of the human getting too close to the robot, resulting in a near collision. So near collisions were just a type of outcome that we used for convenience in these scenarios, just because they're a little bit easier to program. But for every time I say near collision, you could think of something even more drastic, like an actual collision. Essentially a very bad outcome that if the robot enters a risky state, can sometimes happen without the robot being able to control it. And then finally, in this top right video, the robot has the option of not attempting to pass the human at all. Okay, and in a different scenario, we have this unprotected right turn. So I'm showing all of the video outcomes from it, from the demonstrations, but just focus on these bottom two. It's similar to the left turn scenario, and similar actually in decision structure to the overtaking scenario. Essentially, we have these 5 outcomes, and only the contingent plan, which corresponds to the bottom videos, leads the robot to reach the goal of turning right quickly and safely. Here, the contingent plan brings the robot into the intersection, waits to observe whether or not the human yields to the robot, and then proceeds with the turn if so. And essentially, without this contingent plan, this ability to produce a contingent plan, you'll end up with a passive robot or an aggressive robot, as shown in the top videos. And then finally, we have the left turn, the unprotected left turn scenario I showed you before. Okay, so here's an overview of our method from model training to deployment. So the model is learned from multi-agent demonstrations paired with high-dimensional observations of the environment. And then, so for this model, we use the same learning technique as in the original precog model, except now the visual input is an RGB image. So we have this sort of offline training stage. We have this behavioral model as output from it. And then we use that behavioral model as part of the planning criterion at test time. And so, yeah, at deployment, the robot repeatedly plans using this contingency planner, which takes that learned model's density function as input, but also serves essentially as the search space for the policy parameters. The contingency planner also contains that user likelihood, or the user specified goal likelihood function that evaluates joint trajectories. And this can be pretty simple, essentially just rewarding the robot to arrive at some specific destination and penalizing it if it comes too close to other vehicles. Otherwise, it doesn't really have any other more sophisticated terms in the reward, like if you, for instance, like rewarding it for obeying traffic laws or typical velocities that you might get out of the vehicle. These kinds of things are kind of what we expect the model to internalize from the training data. And so basically part of the task of planning is offloaded to the behavioral model, and then the remainder of essentially like selecting a goal is that needs to be contained in the goal likelihood function. Okay, so as output, the planner outputs this state space policy, which is then used to produce the single next target position of the robot, which we then track with a proportional controller on vehicle throttle, brake, and steering. And we execute that controller for several steps before then we rerun the planner. So what we did was we compared our contingency planning approach against a few other approaches in these scenarios, these closed loop control scenarios we set up. And we measured whether each approach can reach a goal, denoted RG, and reach it quickly and safely, denoted RG star. So in order to perform well, the robot has to recognize what sort of situation it's in based on its visual and positional input in order to generalize beyond the training situations. So we had, for each of these scenarios, we had a set of different locations that it was trained and tested, trained and evaluated in. Okay, so what we found is we observed essentially the expected failure modes of each of the non-contingent planners. So I'll step through a few of them now. So the single agent baseline is from our iClear 2020 paper that uses just essentially a single agent model, not explicitly modeling the other agents, as basically as a planner. And essentially what it does is it reproduces with some frequency risky behaviors that are seen in the training data, because it doesn't explicitly model the uncertain behaviors of the other agents, and therefore it can't plan to be contingent upon different realizations of the uncertain behavior of the other agents. So essentially we have some bad data in our training data, and because we can't filter that out with the goal likelihood, the single agent planner reproduces that behavior with some probability. And then for the other non-contingent planners, we have different ways where we can use this joint model of behavior incorrectly for planning. One in which we plan joint trajectories for all of the agents. These are not contingent plans. This is basically assuming you can control all of the agents, making the erroneous assumption that you can. And then this results in essentially like overconfident behavior by assuming essentially every other vehicle or every other source of uncertainty in the scene is going to respect the robot's wishes. And then there's this other non-contingent planner, the one that plans only in the trajectory space of the robot, which is going to be too passive because it doesn't take into account the ability for the robot to react differently to different uncertainties in the future. And so that causes, for instance, in the left turn scenario, the robot to wait outside the intersection until it's guaranteed the human-driven car, the source of uncertainty, has passed through the intersection. Okay, so we have this we've seen our way to learn a planner for driving in multi-agent scenarios. But what happens if we try to use it when our robot can't sense relevant agents? So what would our robot do at a so-called blind intersection where it can't perceive an oncoming car? We can treat this as a source of uncertainty, not in behavior, but in sort of perceptual uncertainty. Is anyone there? A good human driver in this scenario probably would slowly inch forward to improve their visibility of the oncoming traffic before deciding whether to proceed. So this type of reasoning we might think of as kind of a natural human behavior, but it's also critical to safe and efficient decision-making, this gathering of information. But it doesn't exist in many real-world autonomous systems, this type of planning. So can we develop an approach in which this type of information gathering occurs naturally, so when needed, as part of a machine learning-driven planning framework? And so that's the goal of this next work, which will appear at CORAL 2022 in a couple weeks. Okay, so one way to view our task is that of learning a plannable model of two different types of uncertainty. Uncertainty in the existence of other agents, as well as uncertainty in the intention of the other agent's behaviors. We can view these as discrete and continuous uncertainties in sort of like a hierarchical model of uncertainty. So there are two ways to think about what we want planning with this model to do. The first is that we want it to plan contingencies for hypothetical agents. And another more general way of thinking about our planning is that it should essentially invoke information gathering to resolve that perceptual uncertainty. So those are kind of two sides of the same coin. Let's look at now how we can adapt our previous model to try to solve this problem. So in our previous work, the goal was to learn a model of multi-agent behavior that can be used for contingency planning of already observed agents. The approach learned from expert observations or demonstrations of reasonable behavior, and then planning was performed by optimizing the for the Z variables for the robot under the uncertainty of the other agent's behaviors. So in order to learn a model from observations, we extended this model to additionally model the detection of other agents as a function of the past positions of all of the observed agents. So by modeling detection instead of existence, it allows us to simply mask out the positions of any undetected agents during training and model inference. So instead of predicting positions as a function, basically positions of all the agents jointly, we're also predicting whether or not our ego vehicle can detect each of the other agents. So like before, the model is conditioned on an observed ego agent trajectory from the past, as well as perceptual information from the scene. And so in our model here, we used a LiDAR range map as the perceptual input. This setup allows the model to associate patterns in perception, like potential occlusions, with potentially dangerous unseen agents. So when we use it for planning, it provides agency over this perceptual uncertainty. The robot can plan to influence future detections. So this diagram shows a bit more information about how the model is implemented. The model architecture is similar to the previous model, and then the major difference is this inclusion of the predictions of agent detection. So on the right, we see 3 joint trajectory samples from the model. The top sample shows a joint trajectory rollout of a potential future in which no other agent appears. The bottom samples show different possible futures in which another agent is detected and either is or is not yielded to by the robot. So in order to evaluate our method, we designed some more benchmark scenarios in the CARLA simulator. Each scenario involves a potential occlusion that requires the robot to be reactive in order for it to perform well. This potential occlusion is constructed so that it causes the version of the planner that doesn't reason about occlusion to fail. So benchmark of these types of scenarios with visual input, basically with the high dimensional perceptual input, didn't already exist. So we had to create it ourselves. So I'll show a few outcomes now from the two-car intersection example. So on the left are two possible expert outcomes in which the expert slightly reduces speed as it approaches the intersection in order to give it itself an appropriate amount of stopping time. And then the video on the top right here illustrates an overconfident outcome, which acts as if there will not be another vehicle that can enter the intersection in front of it. But this outcome, in this outcome, there actually is another vehicle that was occluded, and it results in occlusion. So we have this same sort of structure of having underconfident, overconfident, and optimal or irrational behavior, in which different versions of the planner can basically adopt these styles of behavior. So we constructed 4 of these types of scenarios in CARLA and compared our approach against 4 baselines. So each scenario consists of 30 randomized trials. So in each trial, we measure whether vehicle, again, reaches the goal, denoted RG, and reached optimally, denoted RG star. When the vehicle doesn't reach the goal, it's because it collided with the other vehicle. We also measured the collision frequency of each approach, as well as the average time to goal of each approach's successful runs. So the overly conservative reference driver, which we implemented by hand deterministically, always reaches the goal, but never reaches it optimally. So this serves as a reference for the average time to goal. The single agent model baseline, which is again from our iClear 2020 paper that uses a normalizing flow as a planning cost function. It doesn't model the other agents and therefore is expected to reproduce with some frequency risky behaviors seen in the training data because it doesn't model on uncertain behavior of the other agents and therefore can't plan to be contingent upon different uncertainties, including the perceptual uncertainty. Okay, the multi-agent model from our previous paper doesn't model the potential appearance of currently unobserved agents. So this causes it to also perform some risky behaviors because it doesn't model uncertain perception and therefore cannot plan to be contingent upon the appearance of currently unobserved agents. Basically, it's overconfident in the quality of its plan because it fails to take into account the potential appearance of other agents. And then we also included a 2-agent so-called game theoretic active perception planner that has been applied to some of these similar scenarios in the past. So this planner assumes perceptual pre-processing and hand-defined models of behavior, so it's not learned, and it also doesn't process raw observations. So it treats the planning problem as a 2-agent zero-sum game. So in order to apply it to scenarios with more than 2 agents, which was this final 3-agent intersection, the planner has to, the way to extend it is to solve multiple 2-agent games by assuming each solution is independent, which also leads to overconfident behavior. And then finally, we found that our main method in these scenarios was able to achieve near expert level behavior overall, which means that it was able to realize an accurate model of behavioral and perceptual uncertainty that it could use for planning. So one promising direction of future work would be the automatic construction of a much larger benchmark of these types of difficult planning scenarios with more variation in the number of agents in the scene, as well as more variation in the types of scenarios that require this type of contingency planning. Okay, and that's really all that I wanted to talk about today. So to read the paper and get the code for that second paper, once we release them, or once we release the code, go to our project page on Google Sites called Active Visual Planning. And yeah, thanks. I hope you enjoyed the presentation.